Okay, in this podcast we're going to talk about the concept of free energy and how it relates to batteries. So free energy, you might have heard of in biology. It is sometimes called Gibbs free energy, and it's defined as the free energy that is available to do work. Okay, so as you know, voltage is the way we measure the electromotive force in the battery, and a volt is a joule, which you could consider to be ability to do work over the charge, having to do with how many electrons are being transferred. And of course, if you're running a battery, you're doing work, right? So free energy can be used to discuss the work being done by a battery. All right. So free energy for a redox reaction can be found by using the equation where delta G, which is the change in free energy, and the naught means you have standard conditions, right? And standard conditions in the case of solutions in metals would mean 1 molar concentrations, 25 degrees C. And that equation says the free energy, the standard free energy is going to be minus NFE, or minus NF. Okay, so N is simply the moles of electrons transferred. F is known as the Faraday constant, and is attributed to Michael Faraday, and it has a value of 1 Faraday is 96,485 coulombs, which is a measurement of charge per mole of electron. And the E naught is the cell voltage, again under standard conditions, and of course, like we just mentioned, voltage is joules per coulomb. So we can measure the standard free energy of a battery using this equation up here. Right? Okay, let's take a look. So it's important to know that in order for a reaction to be considered spontaneous, and by spontaneous it means it will work, it will occur naturally. It doesn't require some external power source to make it happen, like water coming down a waterfall. It happens spontaneously. You don't have to push the water over. It happens because of the potential energy difference. So if the free energy change is less than 0, or in other words, if it is negative, if you have a negative delta G, that means you have a spontaneous reaction. Now we'll talk all about this in Unit 5, and that'll make sense why it's negative. We can also say, though, if that we have a positive EMF, or as measured through the number of volts, if it is a positive number, that we also have a spontaneous reaction. So if delta G is negative, or the EMF or the voltage is positive, we will have a spontaneous reaction, which means the cell will operate, the battery will operate without any external power source. Okay? So they must be spontaneous in order to work without a power source. All right. So we're going to take a look at a specific reaction. So let's say we have a problem where we have to calculate the standard free energy change for the following cell. It involves zinc and copper. Okay, so let's say you're given these values. You're not given a table, which is the way I think it's going to show up in the AP exam. You got to look and decide which one's going to be reduced and which will be oxidized. So the one, remember, all of these are listed as the reducing potential, right? Their voltage when they're undergoing reduction, so they're written as reductions. So the one that has the more positive, or the higher voltage, is going to be the substance that gets reduced, and the other will be oxidized. But of course, if it's going to be oxidized, we have to rewrite it to go the other way. So in this case, it's going to be zinc solid going to zinc 2 plus 2 electrons, and that's going to be an oxidation. And we're going to change the sign to 0.76 on the positive, and when we want the total cell, we are going to add these together. So these are standard, so this would be E naught, right? E naught is going to be 1.10 volts. Okay, so let's go ahead and use the equation we just learned. So delta G is equal to the negative of NF E naught. Okay, and this is delta G naught. So first thing we're going to look at is how many electrons are being exchanged. And in this case, we're gaining 2 electrons on the copper, and we're losing 2 electrons on the zinc. So we don't have to make any adjustments there. So my number of moles of electrons is 2. So I'm going to start over here. Negative, I have 2 moles of electrons. That's my N. My F is a constant. It's 90. Let me see, it's on the equation sheet. I believe it's 96,485. Yeah, 96,485 coulombs per mole of electron. And I'm going to multiply that times E, right? My standard EMF, and this is in volts. And volts, as we know, is joules per coulomb, right? So this would be times my 1.10 joules per coulomb. And you'll see how nicely all the units cancel. Moles of electrons, coulombs, and I'm left with joules. And if I punch that into my calculator, let me see, I have 3 sig figs here, so I'm going to use 3 sig figs, and my answer, my calculator says 212, 267 volts, or joules, so it's going to be 212 kilojoules. And this is negative, because this is a negative mole of electron times Faraday times E naught. And because this is negative, it is spontaneous. Delta G naught, if it is negative, it means it will be spontaneous. Doesn't mean it will be fast, but it means it will be spontaneous. Now we also know, because E naught is positive, because it's greater than 0, because it is positive, that also indicates spontaneity. Okay, that's going to do it.